Hello everyone, welcome back to a new Pyro Math lesson. Today we'll be discussing Pascal's identity. Now Pascal's identity is a mid-math counts level topic. It's also covered in mid-AMC to low AIME problems. Pascal's identity is a combinatorics subject, also known as counting and probability. Pascal's identity has a wide range of applications to proving other combinatorial identities and theorems, and it's used in contests to simplify calculations. So let's get into the equation itself. Okay, so here we have n chooses k. If you're unfamiliar with the choose function, I'll put some links in the description to learn that. It's very important for this topic. So we have n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. And as Pascal's identity's name hints, it's related to the Pascal's triangle. And this visually helps us understand the intuition behind the theorem. And so in the Pascal's triangle, one property is each element can be written as the sum of the two elements in the row above it and next to it. So here, 4 is the sum of 3 plus 1. Another example is 35 over here is the sum of 15 plus 20. And this is consistent throughout the triangle. Another fact that we know is the elements in Pascal's triangle can be expressed as a combination. So first we check which row it's in. So I'm going to use the example of this 10 right here. And we always start in row 0. So this is row 1, 2, 3, 4. And so the 10 here is in row 5. Okay, and 10 is equal to 5. And to figure out what the denominator of the choose function is, we count off the elements in the row. 0, 1, 2. So 10 is equal to 5 choose 2. And if you plug in the formula, you'll get that this is true. And so what we have here is the two facts of a Pascal triangle, and combining them gives us this identity. And let's look more into the proof of the identity other than the intuition we gave before. And first, let's do this through algebra. Algebra gives us a straightforward method to proving it, and will be easy to start off with. So before we do that, we must recall that the formula for a combination a choose b is equal to a factorial over b factorial times a minus b factorial. And if we write the identity using this formula, so I'm just going to write one side of it. If we use the formula here, we have n minus 1 factorial, just doing the first combination, is equal to k minus 1 factorial times n minus 1 minus k minus 1 factorial, which is just n minus k because the negative ones cancel. And then onto that, we add the second combination, which gives us n minus 1 factorial times k times n minus 1 minus k factorial. And here all we did was plug in the definition of the choose function. And now we can do some factoring magic. We can factor out the numerators of the two functions. I'm going to move over here for more space. So we have n minus 1 factorial out of the numerators. And then we just write the denominators again. Apologies, there should be a factorial there. Times n minus 1 minus k factorial. And this still looks messy, so we think we can do more factoring. And to do more factoring, we have to notice the following definition, you could say. Let's take an arbitrary positive integer x. And so x factorial is defined as x times x minus 1 times all the way to 1. And what we can do with this is we can rewrite it as x times x minus 1 times all the way to 1. Right? All we did was just put a pair of parentheses in there, square brackets. And this is equal to x times x minus 1 factorial. And now we can use this to further factor our equation here. And, okay, just rewriting what we had before. We can use it on the n minus k factorial here, because n minus k factorial would be equal to n minus k times n minus k minus 1 factorial. You can also use it on the k factorial here. So k factorial equals k minus 1 factorial times n minus k minus 1 factorial. just like that. And so when we factor, we need common terms. Here we have n minus k minus 1 factorial. Here we have n minus k minus 1 factorial, k minus 1 factorial, k minus 1 factorial. If we bring those all outside of the parentheses, n minus 1 factorial times k minus 1 factorial times n minus k minus 1 factorial. And if we take those out of the fractions, we're left with something a little more simpler. And now we can use our common denominator tricks from algebra to rewrite this as divided by k minus 1 factorial times just rewriting what we had before and getting the common denominator. And note we can simplify some things. There's a negative k, positive k, that's gone. And then using this kind of definition thing above, k times k minus 1 factorial is k factorial. So these guys pair up nicely. And then n minus k minus 1 factorial times n minus k is n minus k factorial. So these guys pair up nicely. And so using all of these tricks, n minus 1 factorial times n divided by k factorial times n minus k factorial. It's already getting neater. And then using the trick thing above, you have n factorial over k factorial times n minus k factorial. Now this is the definition above there, and just applying that kind of backwards, you get this is equal to n choose k. And we started here with one side of Pascal's identity and ended with n choose k. So this is the algebraic proof to Pascal's identity. It's pretty straightforward. And I also want to highlight another way that we can prove this. And this is called the counting argument. Many combinatorial identities have a more logical way of thinking about it. And here we're going to use something called a committee argument. It's another form of counting argument, except it follows this specific pattern. So let's dictate the situation here. Let's say we have a nation with n people, and out of those n people, we have one king, and then we have n minus 1 peasants. And we want to form a committee out of these n people. We want a committee of k people. So out of these n people, we want k people. And we already know one way to do that, right? It's just the definition of the choose function. So we have n choose k, and that gives us the number of ways to form a committee of k people. And what we do with committee arguments or counting arguments is find 2 ways to solve the same problem. And that gives us an equation, because if we have 2 ways to solve one problem and they give different looking formulas and they're equal, then we have an identity. And so that's what we're going to try to do here. Form a specific argument or scenario where we can derive the Pascal's identity. And we already have n choose k, which is part of Pascal's identity. We just need the other side. And to do this, we use the following argument. We use 2 cases motivated by the 2 terms in Pascal's identity. So case 1, let's just say the king does not want to be on the committee because he's a busy king. Okay. Well, then that changes things. We're left with n minus 1 peasants in k spots. And so for case 1, the number of ways when the king does not want to be on the committee is n minus 1 choose k. Now case 2 is similar, but the king wants to be on the committee, right? He has 2 choices. He can be on the committee or not on the committee. And so he's already guaranteed a spot as the king. And so what happens? Now there are still n minus 1 spots left. There's n minus 1 peasants left, but only k minus 1 spots left because the king took one. And so the number of ways in this different argument is the sum of the only 2 cases. And look at that. This is equal to the first argument. So this is the first argument. And this is our second argument. And we can just equate the 2 arguments because they count the same thing, the number of ways to form a committee of k people. And so that's another proof of Pascal's identity using a counting principle and logic behind counting. So that's it for this video. I hope you enjoyed and will join other pyromath lessons. Thank you.